Hi there, this video is just a quick overview of how we use Slater determinants as an easy way to construct multi-electron anti-symmetric wave functions. So we saw in class that one of the requirements for us to have an acceptable wave function for a system is that we need to have what we call an anti-symmetric wave function. So that stems from our Pauli principle. So that just tells us that upon the interchange of any two rows or columns, that the sign of our function has to change sign. Okay, so easy enough to do when we're just dealing with one or two electrons, but once we start getting into more electrons in our systems, it becomes really cumbersome to try to put those together. So that's where Slater determinants come into play. So these Slater determinants that are set up like this are really just useful shortcuts to help us put together our anti-symmetric wave functions. Now, each one of these matrix elements inside this determinant, so our determinant is signified by these long straight brackets. Okay, so inside here we call these matrix elements. Okay, each individual term is a matrix element. Those U's are shorthand for our spin orbitals. Okay, so each U is a spin orbital. Remember, a spin orbital contains both a spatial and a spin part of our wave function. Okay, so this first term here would be a 1s 1 alpha 1 spin orbital. This term here would be a 1s 2 alpha 2 orbital, so on and so forth down the line for as many electrons as you have. As we move over to our second column here, okay, there we're just basically occupying our next position. That's possible for an electron, so that would still go into a 1s orbital, right? Because remember, we have room for 2 electrons per orbital in the spatial part, but then we need to switch the spin, right? So we have to pair our electrons. So in this column, we would have the only difference there being that we're giving spin downs, those beta spins to each electron. Okay, and then you would just fill in across for as many electrons as you have, okay, gradually filling up each orbital from lowest energy to high. Okay, so the nice thing about these determinants is that they help to guarantee the certain requirements that we have on our wave function. Okay, so specifically, the sign of our determinant will change when we interchange any two rows or two columns of the determinant. So that essentially is the same thing as saying that it satisfies our Pauli principle, right? So when we interchange any two rows or two columns, that's the same as saying we're interchanging any two electrons with one another. Okay, when we do that, we need to have that anti-symmetric situation where the sign of our function changes upon the interchange of any two electrons. Okay, so the determinant satisfies that. So maybe we'll do some examples, but take a minute after we do those examples and satisfy yourself that if you change the position of any of those electrons, so say you change position 1 and 2 here, so put 2 up here and 1 down here, satisfy yourself that the sign of your function is going to change. Okay. The other requirement that is satisfied by using the Slater determinants is that if any two rows or columns are the same, then our determinant is equal to 0. Okay, so that essentially just satisfies our Pauli exclusion principle that says no two electrons can occupy the same location. Okay, can't have the same 4 quantum numbers. So this one would be our Pauli principle. So that's our anti-symmetry requirement. Okay, and then this one would be our Pauli exclusion principle. Okay, that's our no two electrons can have the same for quantum numbers. Okay, so both of those requirements are satisfied just by using this determinant method to put together our wave function. Okay, let's do an example on how we would put together one of these Slater determinants. So let's start off nice and easy with our helium atom. Okay, so we know that we have 2 electrons there. So what we would say then is, we would have a wave function dependent on 2 electrons, so electrons 1 and 2. That's how we note that. Okay, and then we want to put in our normalization constant prefactor there. Okay, so that depends on the number of electrons that you have. Okay, so that's going to be 1 over n factorial. So in this case, that would be 1 over 2 factorial. And then we take the square root. Okay, and then we have our determinant. Okay, so again, we have 2 electrons, remember, for helium that we're dealing with. Okay, so that means we're going to have a 2 by 2 determinant. Okay, so we'll have 2 rows and 2 columns. All right, so now we put in our spin orbitals. So the first orbital that our electron goes into for a ground state, so remember these are going to be for ground state electron configurations. Okay, so lowest energy orbital we go into is a 1s orbital, so that's going to be the first spatial orbital that we fill. So we have a 1s1. Okay, and then we just have to assign a spin part of our orbital as well. So convention is to start with the spin up, the alpha. You could very well start with beta. Okay, it really is an arbitrary designation, but convention is to go alpha beta order. Okay, so we will say 1s1 alpha 1. Okay, and then we will do the same thing for electron 2 down here. So the next row we'll deal with electron 2, so we'll say 1s2 alpha 2. Okay, so just remember, going down the rows here, you're just changing the electron that you're putting in there. Okay, so you'll go 1, 2, and then if we had 3, 4, okay, that would change for your rows. Okay, so then we want to account for any other options that are possible for electrons to go into. Okay, so we know that both electrons in our ground state will be going into our 1s orbital. Okay, so that's still going to be our other option, but we know that we also have another spin option. Okay, so we know we need to account for the beta spin or the spin down option. Okay, so we're still going to have a 1s spatial orbital. Okay, and so we still have our 1 electron in that 1s orbital, our first electron in that 1s orbital, but then we're going to say it can also be spin down. Okay, so here what we've done is we've accounted for in this whole row here all of the options for electron 1. So electron 1 can be in the 1s orbital spin up or the 1s orbital spin down. Okay, and that's all we have for the ground state for our helium atom. Okay, so remember, we're filling the lowest energy orbital, so we're only dealing with the 1s orbital here. Okay, then we'll do the same thing for electron 2. So electron 2 also has a similar option, so it can be spin down as well. So now we have accounted for all of the possible options for electron 2. Okay, so electron 2 can be in the 1s orbital spin up, and electron 2 can be in the 1s orbital spin down. Okay, so now with all of these matrix elements, okay, we've now essentially accounted for all of the possible options for electrons 1 and 2, right? They can both be in the 1s orbital, and they can both be spin up or spin down. Okay, so this is how we're basically satisfying our indistinguishability requirement, right? So remember, all of our electrons are identical. They all need to have equal opportunity for occupying all of the possible orbitals or spin orbitals that are available. Okay, so now we can practice evaluating this. So if this is not something that you have done recently, and remember back to our math quiz at the very beginning of the semester. Okay, remember to evaluate a 2x2 determinant. You're just going to take essentially the cross terms here. So we're going to multiply those two, and then we're going to subtract these two. Okay, so 2x2 determinant evaluation is really easy. So we can do that quickly. So we will have our, don't forget your normalization constant. So 1 over the square root of 2 for this situation. And then we take our cross term. So we end up with 1s1 alpha 1 times 1s2 beta 2 minus these ones, okay, those cross terms. So then we get 1s1 beta 1, 1s2 alpha 2. Okay, so this would be your full wave function, and just to kind of put it into a form that looks familiar to you from when we first looked at the helium atom, we can factor out here. Both of these terms have a 1s1, 1s2 term. Okay, so we can just factor that out. So we would have 1 over the square root of 2, keep drawing this a different way, but that's fine, times 1s1, 1s2, and then we have our spin, so here we'd have alpha 1 beta 2 minus beta 1 alpha 2. Okay, so hopefully this form looks familiar to you from what we were playing around with in class. Okay, so we did not have this normalization constant out front. We kind of ignored that, but that should be in front of all of your helium atom normalized wave functions. Okay, so here we have our spatial part of our wave function, and then this would be our spin part. Okay, so remember, if we think back to the helium atom, we said, okay, so both electrons can be in the 1s orbitals, so this designation is totally fine. Okay, this form of our notation is fine for the spatial part, right, because we're not distinguishing between electrons here. We're saying that both electrons 1 and 2 can both be in that 1s orbital, nothing distinguishing them there. Okay, here, right, this would be our linear combination of the spin options. Okay, so remember, we can't specify that electron 1 is spin up or electron 2 is spin down, right? Or that electron 1 is spin down and electron 2 is spin up. Okay, we have to take the linear combination of all of those possibilities in order to get a satisfactory result. Okay, and then we saw that we need the negative option in order to satisfy our Pauli principle of anti-symmetry. Okay, remember that's our experimentally determined factor. Okay, that's why we take the subtraction in that linear combination. Okay, so hopefully this ties together our path to these wave functions for our multi-electron atoms. Okay, so we had started off with this form of our wave function. Okay, we put that together by hand, going through all of our different requirements for having an acceptable wave function. Okay, but hopefully now you can see that you can get to that same result by using that Slater determinant method. Okay, and then just again a little reminder here, this we call our spatial part of our wave function, and these would be our spin parts of our wave function. And then everything together makes our spin orbital. Okay, so all of that is our normalized spin orbital. Okay. All right, now What happens if we have 3 electrons? Okay, you would just kind of keep going on adding to your determinant. Okay, so let's quickly do an example of lithium. Let's just add one more electron. So lithium atom, ground state wave function. So that's going to be 3 electrons. So we want psi of 1, 2, 3 there. Obviously, you're not going to keep writing that as you get into more and more electrons, but we won't generally do more than a few. So we want our normalization constant. So 1 over n factorial, 1 over 3 factorial will go in there this time. And then we start putting in our matrix elements, our spin orbitals. Okay, so just like before, start with the lowest energy and work your way up. So we start with our 1s orbital. And again, by convention, start with your spin up. Okay, and then our next option is going to be still our 1s orbital, spin down. Okay, and then once we have 3 electrons, we need to start moving into additional orbitals. So we've done all we can do with our 1s orbital. We've put 2 electrons in there. So now we would be moving up into our next higher energy orbital. So we would go into the 2s orbital. So we do 2s1, and then again, convention is to start with the alpha. Okay, so can make that the end of our determinant. And now we're just going to fill in for each electron. So here we're going to have, again, that 3 by 3 determinant. So remember, for each one of these, you get what we call an n by n determinant. So 3 rows, 3 columns for our 3 electrons. So now we're just going to put in our other electrons. Oops. Electron 3. Make sure you change your numbers. So electron 2 here. And be careful, it's easy to go on autopilot and start putting in the wrong things. But just do a final check. Once you're done, make sure all of your rows have different electron numbers in them and all of your columns have different spatial or spin orbitals in them. Whoops, I've switched my spins. Okay, see, don't go on autopilot. All right, so make these alpha. Just want to be consistent. Now, it would have been totally fine for me to put betas here in this last column, okay? Again, it's just convention to go in the order alpha beta, okay? There's no good reason for the fact that we have alphas here instead of betas, okay? As long as you're accounting for your different options and you're not repeating your options. Remember, if you repeat any column or any row, what does that do to our determinant? It makes it 0, okay? So that can't happen. That means our wave function 0. That's not very helpful for us, okay? So that's really the one thing you want to look out for, is that you're not repeating your rows at all, or your columns, okay? All right, so this would be our the way that we would set up our determinantal wave function for lithium. Okay, for our 3 electrons. Now, evaluating a 3 by 3 determinant is a little bit more involved than our 2 by 2. I won't generally ask you to do this, although it's probably a good thing for you to know how to do. So, for these, you kind of cross out your first column and first row, okay, and then do your cross product here, and then you'll subtract, cross out your middle column, your first row, do your cross product with these, and then change your sign. You'll add, cross this out, cross that out, do your cross product here and here. Okay, so it's a little bit more involved. Change a sign, and I will just put the result there for you so you can check your evaluation of that. Okay, so here is the magic wand result of evaluating the determinant part of our wave function. Okay, don't forget we still have our normalization constant out there, but right here we're just evaluating here. This is the result for the determinant. So again, just to walk you through how to do that, you would, let me stick with my color coding here. We have our signs, basically like this. So we're going to have positive term for that first set of functions. Then we switch to the negative, and then we switch positive. So you're just alternating your sign for each section. Okay, and then for this first term here, you take, and I think I forgot to mention this in my brief verbal description earlier, we also want to multiply by that term. Okay, so for this first set, we're going to take this term here, and then we're going to basically cross out all of those. So we've got this factor. Okay, so this comes out front here, and then we're going to multiply by what's left over after we cross out the row and column corresponding to that. Okay, so we have our term here, and then this whole thing here is the result of essentially evaluating this 2x2 determinant. Okay, and then we do the same thing for our next column. So change our color coding here. So there, we're going to start with that term. Okay, so that's what's out front here. Remember, we're changing the sign. Okay, so that's where our negative sign comes in there. And then we kind of cross out the row and column that correspond to that. And then we evaluate the determinant that's left over from here and here. So this would make up its own new 2x2 determinant, the result of which is in this bracket here. Okay, and then for our third one, once again we change the sign. Okay, so remember we're back to positive, so we get the positive here, and then we have our third term goes out in front here. Okay, and then again crossing out the row and column corresponding to that, and then evaluating the determinant left over from that, and then that result is in our brackets here. Okay, so kind of hard to describe this verbally, all on one page here, but that's just a quick overview for how you would evaluate a 3x3 determinant. As you can see, as we get more and more electrons, these determinants get more and more involved to evaluate. So generally I would not, in reality, have you evaluate anything beyond a 2x2 determinant. It just gets, as you can see already, just with 3 electrons, it gets kind of annoying. So we would leave that to our computers at that point still. But again, hopefully you can see that by using the secular determinant method, you can create a wave function that essentially accounts for every option, every spatial and spin orbital wave function option for your electron. Okay, so that's pretty much it for our Slater determinants. Okay, hopefully this helps you feel more comfortable putting those together and working with those. Thanks.